An introduction to optics is, in this case, a little developer-centric, so expect some code on the slides, but it's not too hard. So the agenda today is a small overview about optics, then how to program with optics, basically how to set up your scene, how to set up your programs, what's playing together. The most interesting part for people here is probably that I wrote a set of new applications which are going to be published on GitHub in the Optics Advanced Examples repository. So I wrote 9 increasingly complex programs which show everything I'm going to demonstrate today. And once you have seen this tutorial, you can probably work through these examples easily. It's a nice foundation for an own renderer. I'm explaining 2 new features which are new in OptiX 5, which are the motion blur and the deep learning denoiser. So for the people who know optics, the takeaway here is that I'm going to present some methods to make your code smaller, more efficient, a smaller scene graph, and some tips and tricks what the smallest possible scene graphs should be. And starting with that. For everybody else who hasn't used optics, I'm just starting with the concepts. And first thing is, optics is an NVIDIA GPU raycasting SDK. So basically, there's a high-level GPU accelerated raycasting API inside. There's also a low-level raycasting API, which is called OptiX Prime. But I'm only talking about the high-level one here, because I think this is the more flexible one and what you should use in the future. It has a very, very simple C API to set up scene and data constructs. So you are responsible to put together your individual data and your programs. And it's a C API to be able to wrap it with whatever high-level language you're using. So there's a convenient C++ wrapper inside the OptiX SDK already. I'm using the C++ wrapper, so you will see different function names, which are very easy to translate back to the C API. OptiX supports multiple program domains. That means you have control about ray generation, closest hit, any hit, these things, and a programmable per ray payload, so you can put data on an array as your algorithm requires it. So you are responsible for the algorithm, and you can do it. It has a flexible single ray programming model. That means you don't have to care about bundles, you don't have to care about wavefronts. You just think about a single ray. What should it do inside your optics programs, which are the device side programs are written in CUDA, actually. So it supports multi-GPU and NVLink. This is interesting in a form that you can actually have a system with multiple GPUs, and optics will schedule the ray tracing on the individual GPUs. And you select which GPUs to use. And new is if you have a very high-end system with NVLink and the driver is running in the Tesla Compute cluster mode. That means not under Windows WDDM, so under Linux and under Windows in the TCC driver mode. You can actually put 2 boards together, and the scene size can be bigger then because the memory adds up. So the boards can actually exchange data over the NVLink bridge, and you have a bigger scene size to work with. So, as I said, flexible single ray programming model, you are just thinking about the algorithm and you implement whatever you want. It should work with optics. You can download it at developer.nvidia.com optics, or there's the landing page, and from there on you can find it. I have 2 examples which show algorithms I implemented to show that it's very flexible. So this is a volume scattering implementation with dispersion. So if you look at the ear of the cow, you see the rainbow colors, so that's the dispersion. And you see that the light flows through the cow from the left and it gets darker where it's bigger. Optics supports custom intersection routines. So if you have any primitive type, you can intersect. So you need to have a bounding box and an intersection program. You can render whatever primitive you can intersect. In this case, it's hairs. And the shading is also a specific hair shader, which is taken from some research papers. So what do you need? It works on Windows, Linux, and we're trying to make it work on macOS as good as possible. So the last release, 5.0, was a little late with macOS, but we're trying to get it done. So it should be there in the meantime. Since OptiX 4, the supported boards are Kepler, Maxwell, Pascal, and Volta at this time. You don't need a Quadro, it works on any of these chips. You need a disk driver supporting CUDA 9 with the current OptiX version because it's built with CUDA 9. So it's built on CUDA internally and CUDA 9 was used to compile it. You need, of course, the OptiX SDK. You can download it in the links I said before. You need a CUDA toolkit to compile your CUDA code with the device programs to PTX code. So it's from source to source, so it's from high level to assembly. And OptiX takes the PTX source and builds its programs out of it. And you need a host compiler supported by the CUDA toolkit. So if you're under Windows, it's Visual Studio 2015 or 2017, and then you need CUDA 9 because only that supports 2017. If you use CUDA 8, then also 2013 should work. So it's a look in the release notes of the CUDA toolkit which parts work together, and then you can use OptiX. Program domains. So there are specific programs in OptiX you have to implement, and you control the algorithm inside your rendering algorithm with it. Let's say you have a geometric primitive like a sphere. Well, here it's a circle, but think about 3D. It's a sphere. You have to implement a bounding box function, which builds an axis-aligned bounding box around that geometric primitive of each of them. You have a ray generation program where you start your rays. You have an exception program where OptiX will call into if anything goes wrong. And then you start shooting rays. And if you miss all the bounding boxes in your scene, you actually end up in the mist shader. So you have to implement what happens if you don't hit anything. Normally it's black or white or light or anything you want. If you shoot a ray through some bounding box, there will be an intersection program called when you intersect such a bounding box inside the acceleration structure traversal. And what that does is it calculates, so you have to calculate intersections in that bounding box or the geometry inside. And then you call into a program which determines if it's actually visible at that point or if there's a hole inside. And this is the AnyHit program which can decide if it's actually a hit or not. And if you have a hit, you normally want the closest hit, and that's where shading happens. So you see the color coding. The ray generation and exception is per entry point. So you have multiple entry points. So for example, if you want to have a path tracer, you want to have a weighted ray tracer, you want to have ambient occlusion, you can have all these things in one program as different entry points. So different ray generation programs. Intersection and bounding box are per geometry. So if you have spheres, you need one intersection and bounding box pair for spheres. If for triangles, you need another one. For hairs, you need another one. So for each geometric primitive, you need one. And the green ones are per ray type. So you can have multiple ray types in OptiX. For example, one for radiance rays, one for shadow rays, which is actually the standard what you do. And for each of these rays, you have to have programs as you need them. Normally a closest hit for the radiance ray, an AnyHit for the shadow ray, and a mist program to have an environment. And that's it. There's one program missing on this slide, which is the visit program. So there is a dip switch-like functionality in OptiX where you have a selector node and you can select which child in the hierarchy to traverse. And it's seldomly used, so I left it away. If you have a scene with geometric primitives, the bounding box programs needs to be calculated by you, and OptiX will call into your bounding box programs to figure out where your individual primitives are. This is with space redundancy, so the objects are overlapping, so the volumes can overlap, and so there's more volume than actually needed. It's a hierarchy, so it's combining multiple primitives into another box, and then multiple other primitives in this box, and everything together is the root node. And the traversal algorithm starts somewhere at the root and figures out which boxes to traverse with a specific ray direction. OptiX has multiple state-of-the-art acceleration structure builders inside. The builder also selects the traverser, which is used. So you have a BVH traverser, which is the classic thing, which is actually this picture. You have an SBVH traverser, which is a splitting BVH. So it's actually splitting big triangles into smaller parts so that the volume gets smaller. You have a TR-BVH, which is a very fast builder. It's the one which is recommended to be used for almost anything today, because that's the fastest you can get. And there's a no acceleration one, so if you don't need an acceleration structure because you have only one object under your root, then you don't need an acceleration structure, you just traverse that. How does the scene look like in OptiX? If you set it up with the C API, first of all these boxes are nodes in the node graph OptiX uses. The geometry connects the bounding box and the intersection program with your primitives. So basically you have some buffers attached to the geometry, and the bounding box program and the intersection program pick the buffer data and build your geometry, and OptiX calls into the bounding box and intersection routines as needed for the acceleration build into the bounding box, for the intersection during traversal. And each geometry needs to be put under a geometry instance. And the geometry instance combines the geometry with a material node. And the material node defines what the closest hit and any hit programs are for this material. So if you have an ambient occlusion material, then you have different closest hit and any hit programs than complex layered material, for example. So different materials, different closest hit programs attached to geometry instance. You have a geometry group, which combines this with an acceleration structure. So the brown acceleration structure there in the top right is basically building the acceleration structure over all the geometry underneath that group, and OptiX can traverse that. This is your smallest scene setup you can have. It's not getting smaller. You can leave away the AnyHit program maybe, but anything else is required. This is your minimal program or scene setup. You can also instance whole subtrees. So this is the same minimal scene structure as before, but now you can put transforms on top of it, and you have many of the individual subgraphs instance in your scene at different positions maybe. And to put this all together, you have a group node at the top, which also gets an acceleration structure, which builds the acceleration, the high level, so the top level acceleration over all the second level geometry groups. And basically it's only one in this case, over all transforms, because the boxes underneath are always the same. Interesting part here is what you can do with this. The back left image is 1 million of these small preview objects. So they have all the same material. It's like a specular reflection with 10 bounces, and this is like 4 years old. It renders at about 1 frame per second. If you need particle systems, don't do this. So if you need particle systems, use spheres and put them into a buffer and then update just the buffer. This is slow, but you can do it. If you have lots of houses or a whole city, you save a lot of memory if you do this. What is the method if you actually want to have different materials on your objects? This was an image with all the same materials. If you have one geometry but you want to have different materials underneath, or on top actually, you have to have different geometry instances to be able to attach different materials. So material A and material B use the same geometry, because you have two geometry instances with different materials, but both share the same geometry, and both need to be put under separate geometry groups. And now the fun part, the acceleration structure of all the geometry in the bottom can be shared among all the geometry groups using that geometry, because it's the same geometry, so the acceleration structure is the same. And then you can transform that and put it under group as before, so as many as you want. It's the same geometry with different materials, and you can do stuff like this. This is a preview scene with 9 different car paint shaders, and the geometry is only in the scene once, but I'm using 9 different instances of it and have 9 different materials on them. And it's pretty nice. It's an MDL material actually. For this tutorial I wrote 9 new OptiX examples. They start off very slowly and get more complex very quickly, but it's a nice start if you start a new path tracer application. Let's start with the first one. It's OptiX Hello, basically. Everything it does is it renders a green background with OptiX, and you can actually select the color. And this is OptiX Intro 1. And this demonstrates the minimal setup you need to do on the host side. So this is using the C++ wrapper calls. You have to create a context. That's a static function. So it's OptiX context create, and then you have your context. And in the context, you can select which devices to use. The set devices function gets an array of a vector of integers with the ordinal numbers of your installed devices. So it's like 0, 1, 2 if you have 3 devices, and then you say, okay, all 3 of them. You can leave this away, then OptiX will pick all devices it can find which are compatible with the current OptiX version. Interesting to note, OptiX 4 and above support heterogeneous GPU setups. So we can actually have a Maxwell, a Kepler, a Pascal, a Volta board in one system, and it will run on all 4 of them at the same time. Problem is it will build the shaders 4 times. So what else? You need at least one entry point. So if you want to call into OptiX or launch some kernel in OptiX, you would have to have an entry point. An entry point is always a ray generation program. You can create a program from a PTX file or a PTX string. So I picked the file here. So you just have the file name and the program name, and it filters out the program you want from that PTX file you previously compiled with CUDA. You say which ray generation program is which entry point. So it's like set ray generation program 0 is program number 1, which you just created. The index is the entry point. You have to set the number of rays, ray types you implement. If you don't shoot any rays, this is 0, which is actually happening in this first program. You have to set a stack size. So OptiX handles your stack size per thread, per core on the GPU. So if you have 5,000 cores, be careful that you make the stack size as small as possible, because that can be gigabytes if you just say, oh, I need 100,000, and you don't need it, and then it explodes. So make it as small as possible. The current sizes are something below 10 kilobytes, so 1,000 or 8,000. So I'm normally using 1,000 to 6,000 bytes there, not more, unless your algorithm requires it. If that is too small, you will get exceptions from OptiX which tell you that your stack was overflown. So you can detect that it happens and make your stack size bigger or smaller and figure out what the smallest is. We are planning to change that API to just say how many maximum recursions we want in the future, because this is a little awkward. You have to create some buffer. So OptiX uses buffers which can be 1D, 2D, 3D indexed. And this is a 2D buffer with width and height and height. And this is the only way to get data back from OptiX. You must have a buffer, otherwise you can't read data back. You can set this buffer as a variable inside OptiX, and then in the device code you can access that. And then you can launch the entry point with your ray generation program you had defined in the beginning. And here, since the buffer has width and height, your launch is probably also width and height, so it fills the whole buffer. After you have launched and it returned, you can map the buffer, and the level and flex is for texturing. Normally this is 0 and read or write, and read something or write something and unmap, and you're done. So this is the minimum program you have, which is actually the code inside the OptiX Intro 1. This is all. This is really all. This first OptiX program. How does the ray generation program look like in that small thing? So first, you have to declare the buffer on your device side. So this is CUDA code now. OptiX has a RT buffer declaration, which is a template, and you tell what type it is, what dimension. So it's a float 4, 2-dimensional. My variable naming has, I use sys for all variables which are context global. I use the for all, so the prefix the launch index or the whatever intersection distance, to say it's a semantic variable, and you see a declaration of that. So it's an unsigned int2, so 2-dimensional index, and it has a semantic at the end, at the third argument, which is called RT launch index. OptiX will fill in that index because OptiX does the scheduling. You don't know which index comes first or whatever. OptiX picks which rays to shoot, and the launch index tells you, okay, it's this one. The syntax here looks a little awkward because there's a comma and a space behind the semantic. So it's actually type, variable name, semantic, annotation. So behind the last comma, you can actually put user-defined annotations. So in case you want to query these and build a GUI from variables in your code, then you can do that. I'm not using that, but you have to have these 2 commas there, otherwise it fails. So here you see it again. I have a user-declared variable with a float 3, which is my color, and then I have my ray generation program. And all it does is using the operator bracket, so the index operator, to fill in a float 4, which is built by taking the float 3 color background and a 1, and write that out into my buffer. And this is it. This is really the program. This fills the screen with the color background. If you want to debug stuff like the stack overflow size and things, it looks the same. So you have your output buffer, you have your launch index, you have an exception program. RT program is the OptiX definition for a global entry point, basically, in CUDA. And in the PTX code, you will see how that is translated. There is a convenience function, which is called RT print exception details, which prints in a human-readable form what your exception was, like stack overflow, invalid array, all this stuff. And in this case, I write a very, very, very bright magenta color into the output buffer to be absolutely sure I don't miss that there was an error. If you have a progressive renderer and you write just standard colors, they will get averaged away. So I use a very super high HDR color to indicate errors. Yeah, this was your first program, basically. OptiX Hello. It fills the screen with green. Next one. We didn't shoot any rays, so let's shoot some rays. So I wrote another program which does nothing but shooting rays, but in an empty scene. And all you need there is a miss program to figure out you shot a ray, you hit nothing, so you need a miss program. This one is actually a gradient, so the north pole basically is the top color, the south pole is the bottom color, and all it does is write the linearly interpolated color back into the screen. For that, I need to have a projection to shoot rays. Normally, you have a pinhole camera. OptiX examples use that very often, so probably for most people, nothing new. Just to understand how the layout of the buffer is in my implementation, the launch index 00 is the bottom left corner because, yeah, that's the normalized device coordinate at that point, or the index afterwards. And this matches OpenGL texture origins, so it means if I put this buffer into an OpenGL texture, it's upright. If you put it in a D3D texture, it's flipped. You have to make your ray program differently. The size of this is the launch dimension. You need a camera position, which is a float 3. You need a vector which points to the center of that window, and you need a U and a V coordinate, which again, sys is always variables defined at the context in my implementation, and this is your pinhole camera. It's really simple. So for each launch index, you calculate the center of the pixel there, shoot a ray through it from your camera position, done. It's 2 lines of code. How do you trace rays? First, OptiX needs to know where to start tracing rays. You do that by defining the top object where OptiX should start the traversal. In our previous examples, that was the group node or the geometry group. Normally it's a group or geometry group. You can also use a selector. I'm not sure if transform actually works, but normally it's a group with stuff underneath. You define your top level variable name. In this case, it's this top object, and you set the group object into that on your host. So the round boxes are host code. This is the device code. On the device, you can see that variable if you declare it as an RT object, which is a generic OptiX object. And it's the same variable, again, comma, comma, for the semantic and annotations, which aren't needed here. And you build your ray. You have a small function. The ray is basically a structure which has an origin, direction, minimum interval, and a maximum interval value, and you can fill that individually or use the makeRay function. And all you do is fill your ray, declare it. Then you have per ray data, which is a user-defined struct. So you define what the per ray data on that ray should be, and you trace your ray. So this combines all the 3 things. It starts traversal at the systop object with the ray from this origin and direction. The ray type defines which programs inside the material to call. The material can have closest hit and any programs for each ray type. And you say, okay, ray type 0 gets into these programs afterwards. And the per ray data is defined here. And the question is, now I shot a ray, how do I access the data of that ray in the other domains? So, for example, I hit something, or I missed, and the miss program should write a color into the per ray data. How does that work? That's by the variable semantics. So this is the 3rd field in the declare variable thing. And this is a little spoiler because this is the ray for the motion blur, which adds a time. So we just had top object, ray, and PRD. And if you have motion blur, you actually have a ray which has a time. I'm just saying it here because for completeness, and it's used in a later example. The current ray is accessible in the variable you declare with the RT current ray semantic. It looks like this. So you declare a variable, type ray, you give it a name, and the semantic is the current ray. So in the closest hit, any hit, or missed program, the current ray is the one you used inside the ray generation program or other recursive rays in other programs, so you can access that data. Same for the time. You specify the time once, and if you need the time for a different ray, you can access this via current time. The payload goes into the ray payload, or RT payload in OptiX, and it looks the same. So it's per ray data, you user-defined structure, you give it a name, it's the RT payload semantic, you can access the fields in your PRD. And the same works for the intersection distance, which comes from the intersection program, which comes in the next example. Yeah, pretty clear. The current time gets interesting in OptiX Intro 6, I think. So next, we put some geometry into our scene. So I have prepared some routines which can generate a tessellated sphere, a plane, a torus, a box. And I use this to show how to build your geometry yourself. So if you know how to do this, you can basically load any geometry from any other file format and put it into OptiX. And to actually have geometry in your scene, you need a bounding box program for the acceleration structure construction. So OptiX needs this to figure out where your primitives are. The signature is, so I wrote one for index triangles. The signature is a primitive index and 6 floats, which are an axis-aligned bounding box. And you have to have some indices in a buffer where each triangle is defined. You load the 3 vertices from some other buffer with vertex attributes. So how you do this is all your choice. I left it away for brevity. Then you calculate the area of the triangle by cross product length, and then you write the axis-aligned bounding box if the area of the triangle is bigger than 0 and if it's not infinite. So basically, you calculate the minima and the maxima of the 3 floats in each of the vertices, and that's your opposite corners of your bounding volume in axis-aligned coordinates. If that didn't work, then you invalidate the axis-aligned bounding box and everything is not happening in OptiX. It's not visible. Then you need to intersect your geometry. So it's the intersection obviously needs the current ray, because otherwise you don't know what you hit. And the intersection program calculates attributes. It's like vertex attributes in GLSL or in OptiX. And the semantic there is specific. The green attribute is a predefined semantic in OptiX, which says this is an attribute, and the name behind, so normal in this case, is user-defined. So you can name your attributes as you want. You just have to make sure that you can find out which attribute is it in the closest hit in any program. So I explain how that happens. The intersection triangle gets only the primitive the intersection routine for this index triangle gets only the primitive index. You have to figure out where your triangle positions are, the vertex positions. And then you need some variables and a predefined function in OptiX. So you can write everything yourself, but OptiX actually implements a small helper function called intersect triangle. It gets the ray, the 3 triangle coordinates. It returns the face normal, the intersection distance t, and the 2 barycentric coordinates beta and gamma. So these are the second 2. And then you have to call RT potential intersection with the t, so the intersection distance you currently calculated, and this decides if you actually hit the ray inside the test interval tmin to tmax. So when you build the ray, you hit the 2 variables from 2, basically from 0 to infinity. And it says, did I hit something? And the potential intersection would say, yes, it's in the interval. And in that case, you calculate your attributes. So in this case, you would load the vertex normals from your attributes somewhere in a buffer. And then you calculate your 3rd barycentric coordinate and interpolate the normals here, the shading normal. So this writes basically the attribute variable, and you can access that in the other programs. And then you have to send a report intersection, and the 0 in that is the material index. So you can actually have multiple materials per geometry instance, and you can select which material to call here. I've never used that myself, but you can actually have multiple materials and pick which one to intersect depending on what happened in the intersection program if you want to. And that's it. That's an intersection program. And you have to have one of these 2, so bounding box intersection for every primitive type you want to intersect. So spheres, triangles, hairs, whatever. Now, The program I wrote was just showing the the shading normals. So this is the program doing this. So I need to access the array payload because I want to write the color. And I need to access the attribute at my hit position, which is exactly this. So it's the same declaration as in the intersection program, and OptiX matches the type and the attribute semantic you defined. It doesn't even need to be the same name, but I highly recommend to use the same variable name at this point. And, oh, I forgot to make this green. So RT program closes hit, has no return value and no function parameters. And all I'm doing here is calling transform normal function inside OptiX, which transform my object space normal into world space, normalizes it. So the closest hit program has the whole transform hierarchy in the geometry you currently hit accessible. So it knows how to transform that stuff. I highly recommend to make the transform hierarchy not too deep. So 2 layers is recommended. Everything else can be handled on the application side. So this one knows the transform hierarchy, can transform from world to object, object to world, whatever you need. And I just return a color which is biased, scaled and biased to have no negative numbers. And this is it. So this is basically rendering the shading normal. It's a nice debug feature. You probably need this. So. Next program. Let's make it a little bit more interesting. The end result of this tutorial is basically a mini path tracer with global elimination, multiple important sampling, environment lights, important sampled environment lights, white environment lights, area lights, and everything. So we go there one by one. And the first thing is a brute force path tracer. So this one is just shooting rays into the scene with no direct lighting. It hits something, it continues the ray, it hits nothing, path ends. And you see on the left, with a path length of 2, this automatically gives you ambient occlusion if all materials are white. So it's a white environment, white materials, you shoot 2, one ray and another one. From there, a continuation ray, you automatically get ambient occlusion. This example renders at over 200 frames per second on this laptop. So it's very fast because it's no cleverness in that algorithm. Just to show that it's just not ambient occlusion, you can do ambient occlusion even faster by shooting shadow rays from there, but you can color the individual examples, individual materials in this scene, so it's the same scene, just interactively change materials to red, green, blue. And how does that work like? A unidirectional path tracer has an integrator which tracks a throughput value with every hit you have. So basically, if I shoot arrays, so I'm shooting, like every core works in parallel. I'm just showing 2 of them. If you have a big Pascal board, you have like 5,000 rays going on in parallel right now. And they hit something, and the left one reflects to the green cube, the right one reflects to the blue torus, and you see that the sphere is not perfectly white, and so the throughput gets a little darker. Now, the next ray picks up the green from the cube or the blue from the specular reflection there on the ring, and then goes to the ground or to the sphere again, and goes into the environment. So basically a miss. So this is just an example of 2 paths. There can be millions. And in the end, this is a brute force path tracer which does global elimination, and eventually it refines. If you have a small light in your scene, like in this example, it will fail miserably. So I have an example showing how important direct lighting is. The next example, OptiX 5, is actually adding direct lighting. So I implemented a small rectangular area light. Actually, it's a parallelogram, but built with triangles. And I have a white environment light, which is actually, you don't need that as a light. It's for the principle. How does that work? So here's a scene where you can actually see that there's global illumination going on. If you look at the shadow below the sphere, it's green, so that's reflecting from the sphere. I shoot a ray starting from the ray generation, and it's a radiance ray. That means it affects the throughput and the radiance along the ray once it hits a light. In this case, I have to sample for the direct lighting some sample position on the rectangular light with some whatever random number generator and shoot a specific shadow ray. So as I said, the ray has a ray type. In my case, ray generation is always 0. Shadow rays are always ray type number 1. I highly recommend to hard-code these values as defines. Don't use variables for these. Doesn't make sense because you never change them anyway. OptiX examples do this. I want you to not do this. So it's better if it's hard-coded. So basically what the yellow ray, the shadow ray, tests is if there's anything between the light and the hit point on the floor. And in this case, the sphere is in the way and the ray goes straight through. And if you have an any-hit program on this ray type, it would be invoked either the first or the second one. You never know because the traversal in OptiX depends on how the ray is relative to the bounding volume hierarchy. So it can be the first one or the second one. In this case, it doesn't matter. If you have a hit between the light and the position to be lit, you get no light. Doesn't matter if it's transparent or not. The light transport is a global algorithm. In this case, there's no light hitting this floor point. And the any-hit shadow program on the shadow ray is totally simple. All it does is the shadow ray sets a flag that it's not visible and terminates the ray. So only one of the any-hit program invocation will actually happen. Afterwards, it finishes immediately. This is the fastest ray you can shoot. This is also the ray you should use for ambient occlusion. So hit something, shoot shadow rays, get your ambient occlusion. Here's an example of the importance of direct lighting or next event estimation, as scientists call it. What it does is actually it estimates if the next ray would hit a light, and that's why the name is next event estimation. On the left, we see the brute force path tracer. Environment is black, and there's only a small light in the scene. Actually, it's a square meter. But if you sample this 116 or 64 times or 256 samples per pixel, it eventually converges to the correct result, but it takes forever. It's faster because it's not doing any direct lighting rays. But if you compare it to the right one, the first sample is already much, much, much better than 256 samples on the brute force one. So you must have direct lighting in a unidirectional path tracer, otherwise you don't get anywhere. Making this a little more complex. So far we had just a Lambert material, so a pure diffuse reflection. Let's add some more interesting materials. So I added a tinted mirror material on the torus on the right, and I added glass material, which is specular reflection and transmission, and this one actually supports volume absorption. So the ray goes through that material and gets attenuated by the absorption coefficient. And if you look closely, you see the green sphere is glass and the blue box around it is water. So this renderer supports nested materials. So the index of refraction and the absorption coefficients are actually correctly handled going through multiple materials. Actually 4 only, but no of our other OptiX examples do this. So this is the first one. It's not hard, but you probably need it if you have some case like that. So the individual material was only a Lambert material, and now I'm adding 2 other materials. So how does that look like, and how much code do I really need? A block diagram of my closest hit program looks like this. I calculate my state, which is basically the attribute, the normals and tangents and texture coordinates and whatever. I have to sample the BSDF, in this case the Lambert one. If it's directly lit, then I have to sample a light, and then I have to evaluate how the light affects the material, and I have to calculate the radiance by putting all that together. And if I have a different material, I would have to do the same. And the same, just for 3 different materials. I would have to have multiple closest hit programs to implement different materials or different material things. And if you say, for example, MDL has 24 different BSDFs, you don't want to do that, because then you have a closest hit program for every material and all the green boxes are identical code. You don't need that. Yeah, the question is, how can you make that more compact? And the answer is buffers of bindless callable program IDs, which is hard to digest, but the idea is you use one closest hit program for all matching materials. You calculate your state once, and then you sample your BSDF by calling into a function table with some fixed function blocks. In this case, it's the sampling function for diffuse reflection, specular reflection, and specular reflection transmission, and you can add as many as you want. And then if any of these is there directly lit, which is only the case for the diffuse reflection in this case, you sample a light, and that is also, for each light type, a callable program. So I don't have to have the whole lighting function in each of my closest hit programs, because I only have one. And the light sampling is also a callable program. So you need to have the coordinates and everything from the light available. And I have 3 different lights, a constant, an environment light, and an area light in this case. I pick one of them, sample it, and then I can evaluate the BSDF. And this is the same thing again, the same table as the size of the table of bindless callable program IDs is the same as for the sampling, for the evaluation. 2 of them are in brackets, so specular reflection and specular reflection transmission are actually specular materials. You can't evaluate them because the probability to hit a specific light direction or light position is 0, so these just return 0. You can't actually light them, so I never call these. Only the diffuse reflection evaluation is actually used in this case. So just to give you an impression, if you have 100 materials in your scene, if you did it the other way, you would have 100 different closest hit programs. Now you have only one. And you just have to figure out what the parameters are for the individual materials. And you calculate the radius. So this is a really nice way to make your kernel, your optics code smaller. Highly recommended. And while we're at it, just implement some different camera projections. So I have had this pinhole camera mentioned. This is a preview on the next OptiX program I have implemented. I have a lens shader for a fisheye, which is a diagonal 180 degrees full format fisheye, so no circular one. And I have a spherical projection. And this is the fun thing about ray tracing. You can have any projection. So I can have one for VR, I can have one for spheres, for tori. And the spherical one is actually useful because you can do environment light maps from, let's say you have a lighting setup of a studio light with some bulbs and umbrellas, and you can actually bake this into an environment map and use that to light. It's not the same, but it's much faster. How does a bindless callable program look like? So you need a declaration. A callable program ID is basically the ID of a callable program you build with OptiX, and you put that into a buffer, and it's basically only integers. And the type is, in this template, the signature of the function. So it's a return type name and then as many arguments as you have with their individual types and the name of the buffer. And this is basically a function table. Let's say there are 3 functions inside: diffuse reflection, specular reflection transmission as before. And 0 is the diffuse one, 1 is the specular reflection, and so on. So you can just index at will at any point. You can even use this inside the ray generation program. Means this mechanism allows you to implement light transport algorithms which are deferred, like a bidirectional path tracing. So you combine your rays and the ray generation does the integration and the evaluation of everything. So this can be called inside the ray generation program. How does it look like? Here's an example for the lens shader. So basically, instead of RT program, you tell it RT callable program, and you have the name and the return value of that is void in this case, and it gets 5 arguments: the pixel, the screen coordinates, the sample position, which is the jittered unit square sample position, and it returns the origin and the direction. And this is actually the code of the pinhole camera. You calculate your fragment position, calculate your normalized device coordinates, return the origin, which in this case is a fixed camera position because it's always the same point, and the rest is just, as in this picture, your pinhole camera. So now we have reduced the number of closest hit programs inside our implementation. Is there a way to make more efficient use of our scene nodes? So in this case, the materials. In the beginning, we had the material node, which combined the closest hit and the any hit program with the geometry instance. The material node can hold material parameters. If you look at the first line with the closest hit and any hit programs, they have different scopes, and the search order is from left to right. So if you declare a variable at the program level, that's your default, basically. If you declare it at the geometry instance with the same name, the geometry instance variable takes precedence. So you can actually have a default on the program, and if you declare it later, that variable is used. So you can have like a default red plastic, and then the geometry tells, oh, I want green, and it will be green. And you can also put this on the material. And if you do that, you have to have different material nodes in your scene per material. So my choice is the material only contains the programs and the parameters go to the geometry instance, and that means I have only 2 material nodes in my scene. One is for opaque materials and one is for cutout opacity materials in this case, which comes next. So you can actually save scene nodes if you're clever with your parameters where to put what. Next. So far everything was without textures, now we add texture mapping. In this case there's an albedo texture in the scene, so the plane is just an NVIDIA logo, which is a 2D texture. And if you look at the next image, so this is actually a sphere with cutout opacity, means there is a texture which defines that there are holes in the surface. And you see that the radiance rate, so if you look at the green sphere, you can look through it at some points, which is an AnyHit program which tells me, oh, there is nothing, because the texture said I'm transparent. And the same is true for the ray which detects if there's a shadow. So if you look at the floor, you see that the nice soft shadow there from the area light actually gets hardened at the center of the south pole there. Very nice. So, as I said, you need AnyHit programs to figure that out. And in this case, for the cutout opacity, it works like this. This is the texture on this sphere. So the brighter, the more opaque. So it's like an alpha texture. Black means transparent. You shoot rays, and if the left one hits the white texture area, this one will say, oh yeah, the AnyHit program on my radiance ray is like this. It gets the opacity from the texture. In this case, it would be white, so 1 means opaque. And it compares it against the threshold, and in this case, the threshold would actually be a stochastic random number between 0 and 1, but you can also make an alpha test out of this and just have a slider between 0 and 1, and this would get more or less transparent, but I recommend to do it with stochastic methods. And then it calls ignore intersection if the opacity was too small. So if you hit something black, then the opacity is always smaller than your threshold, unless that's also black. And the ignore intersection tells the intersection program, which calls RT report intersection. This would call into the AnyHit program and say, oh no, forget it. It's not visible, ignore this hit. The shadow ray is the same as the other one for the case where it's opaque. So it's like PRD shadow visible is false, means the ray blocks the light and the ray can be terminated. In the other case, if you hit a black area on the texture, you just say, if the opacity is smaller than my threshold, ignore this intersection, and this will actually produce the nice shadows on the ground here. So looking through the green sphere is the AnyHit program on the radiance ray. Having holes inside your shadow is the AnyHit program on your shadow ray. Handle textures. So OptiX has a node which is a texture sampler, and the texture sampler combines a buffer, and the buffer defines what your texture is. So you can have a 1D buffer, which is just width, then it's a 1D texture. If the buffer is a 2D buffer, then the texture sampler will be a 2D texture. You get the idea. A 3D buffer is a 3D texture, and there's a specific flag on 2D textures where you can say it should be a cube map, and then you basically have 6 textures to download in 2D, which is done with a 3D texture, and 6 slices, and then you have a cube map. All these can be mip-mapped, so you can have 1D, 2D, 3D cube map mip-maps, and all the 2D ones can actually be layered. So you can have 2D layers where every texture is the same size, but you have like 20 of them, and OptiX allows to do that. If you want to do mip mapping in ray tracing, you would actually have to have ray differentials, which is another story. And the texture sampler itself has some parameters you have to set. So the wrap mode, like usual, repeat, mirror, clamp to edge, all these things. So cube maps would be clamped to edge so that it doesn't filter around the corner and has seams. And normally you would have repeat as default. You have a filtering mode where you can actually select if it's nearest filtered, linear, and mip-mapped. And so you have 3 parameters, which is, for example, linear, linear, linear would be mip-mapped trilinear filtering. A read mode is which kind of data to return. So it can either be normalized floats or element type. So if you have a float texture, you would read element type and you have a float. If you have an unsigned int 8, so unsigned byte texture, you would normally use a normalized float, so to get a float value between 0 and 1. You have an indexing mode, which is the same as in OpenGL between 2D textures and texture rectangle. So you can index with normalized coordinates and with absolute coordinates, so between 0 and width and height. And on the other side, it's like for the texture features. So maximum anisotropy is if the texture is visible from a slanted angle, you can actually filter more than one texel. If you have MIP maps, then you can actually clamp and bias them like usual. And now comes the important part. Since Kepler, the GPU supports bindless textures. So that means you don't have texture units anymore, you just have pointers. In this case, it's an integer in OptiX, so you can have 2 billion textures basically as indices if that would fit into memory. And this ID can be used in intrinsics in OptiX to access your texture. So basically, it's RT texture 2D or RT text 2D gradient for level of detail, and you have a type name, what type to return, like float 4, float 3, whatever, float 2. Interesting part here is OptiX is based on CUDA, and CUDA doesn't support any textures with 3 components. It has only 1, 2, and 4. Means if you have a standard JPEG texture which has 3 RGB components, you have to put your alpha onto that. Good part is I prepared the code to do that, so the examples can do that. They use Devil to load any texture. They have 50 different functions to build a CUDA compatible texture out of it, so you don't need to program that part. And you can basically load almost all textures, texture format Devil supports, including DDS, so if you have D3D textures. And the texture ID can be used with all the intrinsics to access them. So now we're at the most interesting feature for me in OptiX 5 is motion blur. So you've seen the scene before. We had the sphere with the holes inside and we had a torus on the right. And in this scene, I transformed the sphere to move towards us. And the torus is moving to the right. And while it's doing this, it's making a 100 degrees roll around the motion vector. And this is a progressively refined image of that, and it's filmic quality motion blur, basically. It just needs a little time. It's very quick, actually. So, yeah, it means there are linear transformations and there are scale, rotation, and translation transformations, so they need to be handled differently, but both are supported. I'm using them on transform nodes, so a transform node can actually be made into a motion blur transform node with 3 new functions. So these are the C API functions, RT transform set motion keys, sets your motion position, so I explain that later. You have a motion range where you can say it's from this time to this time. Normally it's between 0 and 1, but you can say if your shutter is just a 20th of a second, then you can say exactly that range. And you have a border mode. What happens if the ray actually is outside that interval? You can select if the geometry should vanish or if it should just clamp. So there are as I said, there are 2 motion key types. One is a linear interpolated 3x4 matrix. So there can't be rotations in that if you linearly interpolate them, because if you interpolate between 2 rotations, in the middle there's a 0 matrix, so it doesn't make sense. This one only works for scale and translation. And for the rotation part, there's a 16-element thing, so it's basically an array of 16 values, which have a scale, rotation, and translation transformation, and the 16 values are these. You have a scaling matrix, which is an upper diagonal matrix, and the Sx, Sy, Sz are the scaling. The ABC in the top are for sharing, so it actually supports sharing of transformations. I didn't use it. And the P there, Px, Py, Pz, is a pivot point for the rotation. So you can actually select around which point your object should rotate. It doesn't rotate around the center if you don't want it. It can also rotate around some arbitrary pivot point. The rotation itself is a quaternion, and the transformation is just the 3 translations. And if you count all these, then it's 16 values, and you have just an array of these 16 values. And OptiX can interpolate between them because it knows how to interpolate. So That's one part. The other part is you can actually do multiple geometries and morph between them. So you have a motion blur between two geometry descriptions with the same topology. How does that work? There's a new bounding box program inside OptiX 5 where the additional motion index is in the signature. So OptiX will call this bounding box program multiple times with a different motion index, and you have to give it the bounding box for that different keyframe. And then it can build the convex hull around this and make the rotation and whatever. And it has three new functions which are similar to the ones on the transform. So you can set how many steps you have so that OptiX knows how often to call into that bounding box function. You can set a range again, which is default 0 to 1, and a border mode again. And one thing I didn't mention, there's also an acceleration property. So once you have motion blur inside your scene, the acceleration on top is automatically a motion blur acceleration. So it's a little more memory there. Also, the other ones get automatically motion blur acceleration structures. OptiX handles that transparently. And if you have many keys, you probably want not the default of only 2 motion steps inside the acceleration structures, but you probably want to have 3 or so. And you can set a new acceleration property on that to change the default. Doesn't matter. In the beginning, you just use the default. So fun things you can do with this. As I said, I have a torus which is rotating, rolling around its movement. And if you have a rolling shutter which goes in that direction from left to right, you can actually have these nice images of movement over time. Each column is a different time. And you get these pictures you know probably from propellers or rotating coins. If you take them with a shutter camera, you get this result. And this is a single image, so it's no progressively refined thing. So next. Deep Learning Denoiser. The newest feature inside OptiX 5 is a built-in denoiser. The top left of the image shows how the image looked if I wouldn't use the denoiser with 32 samples per pixel. And the bottom right corner shows how that looks with the denoiser activated. And you see that the caustic, especially under the sphere, gets much better. It's a little splotchy, but it's not noisy anymore. And it even works on the motion blur quite nicely, because I made it so. The OptiX SDK has a predefined denoiser training data inside, so we have taught it how to denoise images generated with iRay, hundreds, thousands of them, and you can actually, if you have a different rendering algorithm, like for example a spectral renderer wouldn't work that nicely with this denoiser, you can train your own data. OptiX actually contains a denoiser training folder with Python scripts and some explanations how to make deep learning useful for your own images if you have specific rendering techniques which don't work with this denoiser. How does it work? Simple overview, you render some images, and you have 3 buffers basically, a beauty buffer, which is the noisy one, an albedo buffer and a normal buffer, which are optional, can be added to the denoiser. So it only works with the top one if you want, but it gets much better if you render an albedo buffer. The normal buffer is currently not so efficient to improve the denoising even more. The albedo buffer in this case is generated by picking up the color of the first diffuse hit. So if you look at the transparent sphere, it actually went through the sphere and picked up the color of the texture, which improves the denoising, especially if you have high frequency textures behind transparent materials. This works better. I also tried just returning the primary hit color, and that works well as well. And yeah, you have to figure that out for your own renderer. The denoiser is trained with sRGB data. So this one is the linear image, and you have to tone map it to be sRGB range. And the other ones stay the same. And then you throw them into the denoiser and call that, and it gives you a denoised image. And yeah, it's that simple. How does it look in code? This is the code used inside the OptiX denoiser example. So there is actually 2 built-in post-processing stages inside OptiX. One is simple tone mapper, which is, I think, a Reinhardt tone mapper with a gamma and an exposure. You can write your own. I wrote my own. And all that needs is basically to set up a render graph. So you have an input buffer, an output buffer, in this case, the output buffer from the renderer is put into the input buffer of the tone mapper. As the output of the tone mapper goes in the buffer tone mapped, I named it so. It has two parameters, exposure and gamma. And then you have the denoiser, which is a built-in post-processing stage. And this can actually have more input buffers. So you have the input buffer, which is in this case the sRGB corrected tone map buffer. You can have an optional albedo buffer and an optional normal buffer. And the output buffer is of the same size and same format. So all of these buffers are float 4 at this version. These two post-processing stages are put together inside a command list. And the command list can hold actual launches of your ray generation programs. So the first one, the append launch 0 means it's entry point 0. So it's your ray generation at that entry point. In this case, it's the renderer. The post-processor is the stage in the render graph behind that, which does just the buffer output sRGB correction, and the denoiser takes what comes out from the tone mapper and takes the albedo normal buffer and does the denoising. You finalize that command list, nothing happened so far, and then you execute it. So you do this once as long as your width and height don't change. You don't have to rebuild this command list. So if you change the width and height, you have to rebuild that command list because there's no API to change the width or the dimensions. Anyways, it's very quick, and you just execute this command list and it will automatically render your image, tone map it, denoise it, and then you just have to map the denoise buffer and show it. So, small recap. The renderer architecture with everything together is looking like this. I have a single ray generation program. It has 3 lens shaders right now. I have one more in the pocket. And it contains the integrator and builds the output buffer. I have 3 different MIS shaders. Only one of them can be active at a time. I have only 2 bounding box programs because everything I use is index triangles. I have a single closest hit program for the opaque materials and another one for the cutout opacity because that has a different any-hit program. And this one has currently 3 callable programs for 3 different BSDF implementations. I have an MDL renderer which has like 24, and I have 3 different light types, a constant environment, an environmental HDR, important sample environment map, and an area light. I have the same number of sampled BSDFs also in the eval BSDF, but the specular ones aren't used. And I have a single any-hit program in case, on the radiance ray, in case there is a cutout opacity inside the scene. Otherwise, I just don't need it. So, I highly recommend this rendering architecture because it's very flexible, it's small code inside the kernel, and it's rather performant, I may say. So, I'm very happy about it. So, takeaway from today, OptiX is a high-level GPU raycasting SDK with a flexible programming model, which allows to concentrate on the algorithm during development because you have only a single ray to care about. It has state-of-the-art acceleration structures, and they changed over time. So OptiX 1 had totally different acceleration structures than now, and it goes on and on. Our NV research team is very, very bright, and each version got faster and working a little different internally to improve new features. And I presented an easily extendable architecture for global illumination path tracer using OptiX features which are currently available in